The third type of work problem I want to look at is the following. We're going to have a sample of gas of some type trapped within a container. It'll have a pressure and it'll have a volume. And what I want to think about is if you allow it to expand, then some work will be done. And I like to figure out how much work is done. Previously, in the Hooke's Law problems, we had Hooke's Law, which told us the force in terms of some distance, the displacement from the natural position. In Newton's gravity problem, we had Newton's law of gravity, which told us the force in terms of some position. Ideally, we would need some sort of fact like that, but unfortunately we don't have one. What we do have is something called the ideal gas law. The gas inside the container has a certain pressure, P. This will be measured in, say, pounds per square foot. It's a force divided by area. There'll also be a volume, V, cubic feet, or whatever your units have to be. And there's the T, which is temperature of the gas, which is measured in degrees Kelvin from absolute zero. In thermodynamics, they talk about the ideal gas law that says pressure times volume is N times R times T. The N is the number of moles of material that you have. The R is an actual honest-to-goodness constant called Boltzmann's constant. And otherwise, we already know what all these letters mean. If we assume that our proceedings don't change the temperature much, then N times R times T will more or less be a constant, and we can simplify this to an easier to work with form. The form of this law that we'll work with is pressure times volume is a constant. As with Hooke's law and the Newton's law problem, if for a given sample of gas I knew both the pressure and the volume at one particular moment in time, that would be enough to tell me what the constant K is. That's going to be our entry point into these calculations. One other thing that we need to remember goes all the way back to when we first started working with the disk method to calculate volumes. If I imagine I have some circular cross-section or any other shaped cross-section with area capital A, I could think of moving that shape perpendicular to the plane that it lies in a certain amount of perpendicular distance. The disk method was based on the observation that the volume of the resulting cylindrical shape is just going to be the area multiplied by the perpendicular distance. We'll need that fact in a minute. The particular situation that we're going to look at is I've got a sample of gas inside an engine piston. It has to start with a certain amount of volume and a certain amount of pressure. Volume times pressure has to equal constant K, of course. What we're going to do is we're going to let the pressure of the gas push the piston to the right. As we've often done, I'm going to call the amount that the position of the piston head is changed. I'll call that delta x number I. As I go from the starting of the situation to the moment where the piston has been pushed forward an amount delta x number I, this causes the volume to get bigger. The amount that it gets bigger is going to be an amount that is the area of the piston head multiplied by how far to the right we've pushed it. This is the area times perpendicular distance again. Now our problem is we don't have a formula for the force that the gas is exerting on the piston head, so we have to do something about that. Pressure is force divided by area. which of course immediately tells me that the force is the pressure times the area. As we move the piston head, the pressure changes, but the area doesn't. If I think about the amount of work done just moving the piston head in the indicated situation, this is going to be the force acting in that chunk of the motion multiplied by how much I changed position. This is our generic force times distance idea. But now we know something more. The force is the pressure multiplied by area A. But when you multiply three numbers together, it doesn't matter how you group the multiplications, so we're going to be very clever here. This tells me something. I'm going to take the pressure on this little interval. I'm going to multiply it by the number A multiplied by the change in x, but we just said a minute ago that A times the change in x is the amount that the volume changes for this one little chunk of the motion. That is to say, the amount of work done on subinterval number I is the pressure on subinterval number I times the amount of volume that changed during this one particular chunk. At this stage of the game, it'll come as no surprise to anybody what we're going to do. We add up all the contributions. To make our approximation perfect, we take the limit as all of the changes in volume tend to zero, which, if you remember, the change in volume is a constant times the change in x. So this is equivalent to the x's all having their little delta x's tend to zero as well. This turns into an integral. If I can express the pressure as a function of volume, this will be an integral of the pressure with respect to volume. The variable of integration is now going to be the volume, so the limits of integration are going to be the beginning volume, which I'll call V1, and the ending volume that I'll call V2. In a general physics system, the pressure and the volume may be connected by some very complicated formula, but in the scenario that we're talking about, the relationship's very simple. Since pressure times volume is a constant, the pressure is the constant divided by the volume. If I put this into the previous integral, I see that I get something that I know how to integrate. For this particular situation that we find ourselves in, the work is going to be the integral from the starting volume to the ending volume, k over v dv. If I know what the k is, then I can easily figure this integral out. A typical problem of this type is this. You've got a sample of gas. It has a pressure of 30 pounds per square foot and a volume of 10 cubic feet. How much work is done if the volume is doubled to become 20 cubic feet? The first sentence is similar to the first sentences found in the Hooke's law and the Newton's law problem. The point of that first sentence is it's going to let me figure out what the K is. It's a direct calculation. Pressure times volume is K. That means that 30 times 10 is K. K is 300. In view of our preceding comments, I can go ahead and write the integral down. That will give me the amount of work that's done during this situation. V is the variable of integration. The 300 is a literal constant. This integral is easy to do. I could now get the calculator out and evaluate this. Or if I wanted to be a little bit fancier, I could use a property of logarithms that says the logarithm of a minus the logarithm of b is the logarithm of a divided by b. 20 divided by 10 is 2, so I could combine those logarithms and also write it this way if I wanted to. Either way is acceptable. They produce the same results. If I convert this to decimal, I get 207.94 foot-pounds. I've written out 5 significant figures. That should be enough. Sometimes people will make minor variations on a theme in this kind of question just to make sure that you're paying attention. So imagine that initially the pressure was 50 and the volume was 20. If the gas expands until the pressure is 10, how much work is done? You'll see this isn't exactly the same setup as before. I know the pressure and volume at some particular moment. That will let me figure out what the K is, but I don't explicitly at this stage know what the volume at the end is. I know what the pressure is, so we'll have to do just a little bit of manipulating here. First thing, let's figure out what the K is. Pressure times volume is K. I know that at a certain time the pressure is 50 and the volume is 20. That means that 50 times 20 has to be the same as the K number. The K number has to be 1,000, and my law that relates the pressure and the volume says that pressure times volume must be 1,000. Now that I know this, at the end of the situation, the pressure is 10. The pressure started off being 50 and ended up being 10. The volume started off as 20 and ends up being 100. Since we also know what the K is, we know everything we need to know in order to figure out the amount of work done. Whatever units I'm using, the amount of work done is 1,609.44 units of work, force times distance. I've rounded that to 5 significant figures. There's nothing intrinsically hard about this kind of question. You just have to pay attention to what you're actually being told. This has been the last of the 3 different types of work problems that I wanted to look at. I hope that by breaking it up into 3 smaller chunks that it was easy enough. I hope everybody's having a good day. I'll talk to you again soon.